CMS.
Yes.
I know.
Yeah. Right for life.
It's almost not quite enough. Okay, welcome everybody. I'm very pleased to introduce my colleague Csaba Schneider, who's going to give the seminar this afternoon. Csaba's from the Federal University of Minas Gerais in Brazil, in Belo Horizonte, and the title is A New Look at Permutation Groups of Simple Diagonal Type. Thanks, Csaba.
Thank you, Cheryl. So first, let me start by thanking the organizers for organizing this nice event and for giving me the opportunity to be here and to talk here. And so I'm going to talk today about simple permutation groups of simple diagonal type. So let me introduce my collaborators, Cheryl, and this is also joint work with Peter Cameron and Rosemary Bailey. And to motivate my talk, so let me start with something that most of you probably know. So let's look at maximal subgroups of symmetric and alternating groups. So if we look at maximal subgroups of symmetric and alternating groups in the finite case, so suppose that omega is a finite set, and so we want to describe these maximal subgroups. The description of these maximal subgroups is actually well known, and so among maximal subgroups we have these intransitive maximal subgroups, which would be just a stabilizer or a subset of omega. So in this case we write omega as a union of two subsets, and the structure of the group would be a direct product of two symmetric groups. So in primitive maximal subgroups would be stabilizers of partitions. So to save space, I wrote it this way. So in this case, omega would be written as a direct product of two sets. So that would define some sort of partition on omega, where the blocks would be sort of copies of delta, and the corresponding maximal subgroup is the stabilizer of this partition, which is the Reed product of two symmetric groups acting in its imprimitive action. And so then we have the primitive maximal subgroups, and we have four of those things. It is sort of part of the Nan-Scott theorem for maximal subgroups of finite symmetric and alternating groups. That, we have first of all these primitive maximal subgroups of PA type. So PA stands for product action. So here the underlying set omega is written as a Cartesian power of some sort of smaller set delta, and we have that the corresponding maximal subgroup is the stabilizer of this sort of product decomposition of the set, and it's again a least product of two symmetric groups, but acting in a different action. So here the action is actually a primitive action on this underlying set. And then we have primitive subgroups of HA type. So HA stands for holomorph of abelian, and here the maximal subgroup would be an affine general linear group, and this would preserve this sort of decomposition or expression of omega written as some sort of finite dimensional vector space over a field of P elements. And then we have two other types of maximal subgroups. So these are sort of, in the Nan-Scott scheme, we can call these maximal subgroups as some sort of geometric maximal subgroups because they stabilize some sort of geometric structure. If you are more familiar with Aschbacher's classification of maximal subgroups of classical groups, so there also we have these geometric maximal subgroups. And then in the last class, we have the quasi-simple groups, maximal subgroups acting in absolutely irreducible representations, etc. And this is what we have here in the case of maximal subgroups of alternating and symmetric groups. Also, we have these almost simple subgroups acting primitively, transitively, not stabilizing any of these sort of decompositions. But in the middle, we also have this primitive maximal subgroup of SD type, this sort of simple diagonal type. And sort of, so until now, these primitive maximal subgroups of simple diagonal type were not considered as geometric maximal subgroups. So we haven't really considered them as stabilizers of geometric objects. And what I would like to do in this talk is to convince you that the right way of treating these maximal subgroups is really that they are stabilizers of interesting geometric objects that arise from the group structure. I mean, I will tell you what these groups are, so if you don't know, I will give the construction for these groups. And so this appeared, I think, already works of Jordan in the 1870s, some sort of description of possible maximal subgroups, but it's more explicit in the paper of Scott, in which he first wrote down the Nan-Scott, the famous Nan-Scott theorem. But the fact that these, I mean, some of these subgroups are not necessarily maximal, so there are exceptions. Among almost simple groups, there can be certain containments, or for instance, in here, it's a least product in product action. If delta has size less than 5, then it's actually contained in an affine group, so this is not maximal. But whenever there is an exception, so these exceptions are explicitly known by a paper of Cheryl, Martin Liebeck, and Jan Saxwell in 1989. So I will refer to some results of this paper later, so I will just abbreviate it as LPS. So what are groups of diagonal types? So I mean, in here, I wrote these two classes with blue, so to indicate that I will talk more about these groups in this talk. So as I said, so one classes of maximal subgroups are formed by groups of simple diagonal type. So I will explain what a group of diagonal type is. So it's sort of it's a more general construction. So when we talk about simple diagonal type, we use a simple group. So when we talk about group of diagonal type, we use a group which is not necessarily a simple group. So the construction, we start with a group T and a number which is at least 2. And so we want to construct a permutation group. So we set a set omega. So omega will be the Cartesian power T to the n. And so our group, which is going to be a subgroup of the symmetry group on omega. So our group, we are going to denote throughout this talk by GTM. So this means group which corresponds to group T and number m. So this group is really the image of this group. So T to the n plus 1 extended by the automorphism group of T, direct product with the symmetry group on m plus 1 points. So our group is going to be the image of this group inside the symmetric group. So it's going to be the subgroup of the symmetric group induced by this group under this action that I wrote down here. So the action is defined. So I need an element in omega. So omega, a point in omega is an M tuple, where these omega i's are elements of T. So I need a generic element in my group. So generic element in my group will have these components. So it will have an M plus 1 tuple that belongs to T M plus 1. It will have an automorphism of T and a permutation in S M plus 1. And so this element will act on this point omega like this. So the M plus 1 tuple will act like the first component of this M plus 1 tuple will act by left multiplication the same way on every coordinate, and the other M tuples will act by right multiplication coordinate-wise. The automorphism acts uniformly on each of the coordinates, and so a permutation in Sm plus 1, so I'm considering Sm plus 1 as the symmetric group on the numbers from 0 up to m. So this permutation acts like this. So here, in order to describe this action the most sort of simple way, I'm sort of taking omega 0, so omega has m coordinates, I'm sort of taking omega 0 to be the identity element in my group T. And so this is a description of this action of Sm plus 1. It actually requires a little bit of work to actually show that this is sort of well defined, these actions are compatible, and here you do get a copy of Sm plus 1 by this action. So here, I mean, maybe just to notice that if you take a permutation from Sm plus 1, which is a permutation in Sm stabilizing the point 0, then this tau, sorry, there's a mistake here, sigma should be a tau. So this tau, if tau stabilizes 0, then this tau just acts by permuting the coordinates in the sort of usual way how you would do it in a Riesz product, or how a Riesz product in product action would act. Right? So, but there is with sort of an extra, in a way, there is some sort of extra coordinate. And so this is our group. So this is the image of this group in the symmetric group is what we are going to be calling a group of diagonal type. And if this group is a simple group, then we talk about group of simple diagonal type. So this is our group. So what do we know about this group? So here, I mean, this group is acting on the on omega, so it may not act faithfully, and so this group is not going to be isomorphic to all of these, but we can describe this group quite explicitly. So our group is actually, so here the first t acts by left multiplication, then t to the m acts by right multiplication, and whenever you have an element in t which belongs to the center, then these two actions would actually coincide, and so here there would be a kernel for your action which is isomorphic to the center of the group T. So this would be factored out, and inner automorphisms would be included here because inner automorphisms can be obtained by acting by sort of multiplication on the left and multiplication on the right by a pair of inverse elements. So inner automorphisms would be sort of involved here. So what you have sticking out is sort of the outer automorphism group, and of course you have the Sm+1. So this is sort of the broad structure of this group of diagonal type. And why is it called group of diagonal type? It's called group of diagonal type because the stabilizer of this point, so 1, 1 is an element of t to the m, which is our point set omega. So its stabilizer is actually the image of the diagonal subgroup. So this is the full diagonal subgroup of t in t to the m+1. So the stabilizer in this part here would be the image of this diagonal subgroup. And in particular, when t is a centerless group, and this is an interesting case, when t is a simple group, for instance, the center of t is trivial. So here the stabilizer would be a full diagonal subgroup, and this is why it's called a group of diagonal type. And it turns out that these groups are maximal subgroups in finite symmetric or alternating groups. So it's possible that this group lies in the alternating group, I believe, and this is a consequence of this previously mentioned theorem by Cheryl, Martin, and Young. Okay, so this is chapter 1 about maximal subgroups. So chapter 2, so permutation groups and partitions and partition lattices. So we started looking at these groups from the point of view of partitions. And so let me introduce some notation that was suggested by our collaborator, Rosemary, and it's quite common in this sort of area, working with partition lattices. So let's suppose that, so if f is a function, any sort of function from a set omega to delta, so here omega is an arbitrary set, delta is an arbitrary set, so then this function will determine a partition of omega into pre-image sets. So in this partition, two elements are in the same block, if and only if they have the same image, and this partition is going to be denoted by f tilde. And so whenever we write partitions using this sort of tilde, sometimes they correspond to given functions, but if they don't correspond to a given function, we just, we can always construct a function, like the projection function that would be corresponding to this partition. And sometimes, I mean, this f tilde is sometimes called the kernel of the function. This is particularly common in transformation semi-group theory, that they call it the kernel. And another piece of notation, so f tilde omega in brackets, so it denotes the block in this partition which contains this point omega. So omega is an element of capital omega, so there's a unique block in this partition which contains this omega. So this is just notation I'm going to use. And another piece of notation, so p omega denotes the power set of omega, so this is the set of all subsets. And we can define recursively sort of p to the k is the kth power set, is the power set of the previous power set. And so using this notation, so we can observe that, so if omega is a finite set, then the intransitive maximal subgroups are really stabilizers of elements in p omega. whereas in primitive maximal subgroups are stabilizers of elements of p square omega. So these are, so a partition would be an element in p square omega. So can we go further? And I suggest we can. So looking at primitive subgroups or primitive maximal subgroups of product action type, so let's consider a primitive maximal subgroup of product action type. As I said on the previous slide, one of the first slides, so to consider such a group, we have to write the set omega as some sort of direct power of a smaller set gamma. And then the corresponding maximal subgroup would be the least product acting in product action. And here, so what we can do is, so if omega is given to us in this sort of form, so it's written as gamma to the m, we can consider the projection map. So Fi can be the ith projection map, and of course it will have a corresponding partition. So the projection map is Fi, the corresponding partition is Fi tilde, and we can consider the set of these partitions on the underlying set omega, and this is going to be an object in P3. So this is the third power set of omega, and this is not going to be an arbitrary element in P3, so it satisfies certain properties. I mean, first of all, I mean the elements are partitions. I mean the elements of these objects are partitions. This is a homogeneous, I mean, what we call in our language is a Cartesian decomposition, and it's homogeneous in the sense that the cardinality of these partitions is independent of I. So the first, the second, everything has the same number of blocks, which is the cardinality of gamma, right? So it's independent of I, and we have this further condition, which is more fundamental, and this is why I wrote it with red. If you take a block, so what's written down here is that, so F1 omega 1 is the block in the partition F1 tilde, which contains omega 1. So if you take an arbitrary block in the first partition, an arbitrary block in the second partition, etc., you take an arbitrary block in each of these partitions, the intersection of these blocks always contains a unique element. I mean, it's easy to see because, I mean, if you take a element from the first block, it's sort of specifying the first coordinate of this element in this sort of expression. If you take an element in the second block, it's sort of specifying the second coordinate, and so on. And this just says that if you specify each coordinate of this element, then there will be a unique element with those coordinates. I mean, this is sort of a trivial statement, but if you look at it this way, it sort of gives you this intersection condition. So what happens is that we use these two conditions to define our structure, what we call a Cartesian decomposition. So suppose now that omega is an arbitrary set, and we are given a collection of partitions. So here I write F1 tilde, Fm tilde, which are partitions, but I don't assume that they are corresponding to given maps. So they are some sort of, you know, partitions, and this set of partitions is said to be a Cartesian decomposition if the properties 1 and 2 in the previous slide are valid. So I want that this should be a homogeneous object, so every partition should have the same number of blocks, and I also want this intersection property to hold, that whenever I take a block from each partition, then I get a unique element in the intersection. And this definition actually was suggested by Laci Kovács in his 1989 paper on the three decompositions of permutation groups. And as we saw before, so if you are given your set omega as gamma to the m, so it determines a Cartesian decomposition. So this given expression would determine the Cartesian decomposition of omega using these projection maps. But if you are given an abstract set, like an arbitrary set, together with the Cartesian decomposition, then these properties 1 and 2 in the definition would allow you to have a bijection, to construct a bijection from omega into the direct product of these Fi's. And since they have the same cardinality, it would allow you to identify your set omega with the direct power of some sort of smaller set. So this Cartesian decomposition object is sort of an internal way of writing a set as some sort of Cartesian product of smaller sets. And so what happens is that, so what we can prove about Cartesian decompositions is that if you are given a Cartesian decomposition of a set omega, then the stabilizer of this Cartesian decomposition in the symmetric group is going to be a Rees product in product action. The Rees product, this first component can be taken to be the symmetric group, in the full symmetric group in F1 tilde, and M is the number of components in the Cartesian decomposition. And whenever the cardinality, the common cardinality of these partitions is at least 5, then this is going to be a maximal subgroup of the alternating or symmetric group. I mean, here it has to be finite. Sorry, I forgot. No, I did say. No, I did say that omega is finite. So it has to be finite in order to get a maximal subgroup. So, and this last assertion is again due to the results of Cheryl and Martin Liebeck and Jan Saxel in their 1898 paper. 1989. Right, and so what do we have so far? I mean, what we have so far about maximal subgroups is that, so of course, I mean, continuing in this sort of pattern, so intransitive and imprimitive maximal subgroups are stabilizers of elements in P omega and P square omega. This is what we had noticed on the earlier slide. And now we can notice that primitive maximal subgroups of product action type, they are stabilizers of elements in P3 omega. So this is the new observation that we can make based on this sort of this theorem, lemma. So what happens in diagonal groups? So I have introduced diagonal groups for you. And so can we say something similar about diagonal groups? So let me remind you of the construction of the diagonal group. So M is a number, at least 2. So T is a group. And omega is this set, T to the M. And we consider the diagonal group, which I claimed on a previous slide, that this was isomorphic to this group, in this sort of in this action that we have described. And so, I mean, you might think that, okay, so the set is T to the M, so there is a Cartesian decomposition associated with this set, which is given to us as T to the M. And there is, but the point is, or problem is, that this group G, it does not preserve this Cartesian decomposition, which is given to us as the natural Cartesian decomposition of this set, given as T to the M. So this thing that we did using the Rees product in product action, it's not going to work. So what we do instead, we can still define some maps, which look a bit like projection maps, from this set. So our set is omega T to the M. And for every ij, so ij are numbers between 0 and m. So m underline denotes the set of numbers from 1 up to m. Right? So m underline 0 would denote the set of numbers from 0 to m. So for every ij, I different from j, ij between 0 and m, we define these functions, these fij, from omega to t. So omega is t to the m, and we define these functions using these rules. Like f0j would be just the jth projection. So f0j on t, so t is an element of omega, written as t1 up to tm. So f0j would be just jth projection map. fi0 would be the ith projection map, followed by the inverse map. And Fij would be this map. So the value of Fij on T would be Ti inverse times Tj, where T, I mean, this bold-face T is this element of omega. So here, in order to define these maps, especially this one, we have to use that our set original input set T is actually a group. So here the group operation on T enters the picture. And so once we define these sets, so each set will correspond to some sort of partition. Sorry, each map, we define these maps. Each map will correspond to some sort of partition of omega. And what we do is that for each I between 0 and m, we collect these partitions, Fij, so here I is fixed, and j is just something different from I. I mean, notice that we don't define these maps for I equals to j, right? So we define these things, these objects, EI, and the diagonal structure for this group is defined as the collection of each of these EI. So that we have an E0, here E1 up to EM. So we collect these things, and this is what we call a diagonal structure for this group, G. Right? And this is an object in P4. So this is, so notice that everything here is a set of partitions. So these are sets of partitions. So they are elements of P3 of omega, and in the end, this is what we call the diagonal structure, is an element of P4 of omega, the fourth power set, right? And so what we get is the following. So this is actually not hard to see that if we start with a group, so if T was a group at the beginning, then each of these EI is going to be a Cartesian decomposition. So in a way, if we go back to the previous slide, so we notice that, so omega is given us as a Cartesian product of a smaller, Cartesian power of smaller set, but as I mentioned, this is not preserved by the group G, but there is a sort of like a family of Cartesian decompositions, a family of identifications of omega as a Cartesian power, and this family is preserved by the group. So each EI is a Cartesian decomposition of omega. So each EI will allow us to write omega as a Cartesian power. And this group of diagonal type is actually the full stabilizer in the symmetric group of this set of Cartesian decompositions. So we can sort of ask ourselves, so what is the stabilizer of this object? So the group G is a full stabilizer of this set of Cartesian decompositions. And if T was originally a non-abelian finite simpler group, then this group, what we get is actually a maximal subgroup. So a stabilizer of this object, which is equal to this diagonal group, is a maximal subgroup of the corresponding alternating or symmetric group. And this last assertion is again due to Martin, Cheryl, and Jan Saxel. And this previous, I mean, the second assertion that the diagonal group is actually equal to the stabilizer of this object. So in the case when everything is finite, this sort of follows from the first, I mean, it follows from here because the diagonal group would stabilize it, and being maximal would give you that this is actually the full stabilizer of this object. But it's also true, and this is something we proved in collaboration with my collaborators, that it's also true, the second statement, if T is an infinite group. And so if we revisit maximal subgroups of the symmetric group and alternating group, so we find, as we had found before, that intransitive, imprimitive, and primitive maximal subgroups of product action type are stabilizers of elements in P omega, P square omega, P to the 3 omega, and this group, this maximal subgroup of simple diagonal type, is now a stabilizer in P4 omega. So this is, again, as I said, is a stabilizer, a full stabilizer of some sort of geometric structure. Okay, so chapter 3. A little bit more, I would like to say something about diagonal structures in a bit more generality. So the question is, what I would like to address here, that can we define diagonal structures similarly to what the definition of Cartesian decomposition was? You remember that Cartesian decomposition is simply just a collection of partitions that satisfy a very simple intersection property. Whereas in order to define this diagonal structure for this diagonal group, I had to start with a group T, and I had to define some complicated maps. So is it possible that there is some sort of more general diagonal structure concept which has a similarly simple definition as, for instance, the definition of Cartesian decomposition? And the answer is, we don't know. but I mean, what we can do at the moment is we can do a little bit more general. So what we can do, so this is, as I said, so this is the sort of problem. So can we give a general combinatorial definition of diagonal structure? I mean, of course, I mean, we want a diagonal structure to be interesting in the sense that we want that its stabilizer in the full symmetric group should be some sort of interesting group, like transitive, preferably primitive, you know. And at the moment, what we can do is we can sort of generalize this sort of thing that I had presented on the previous slide. So what we can do is, instead of starting with a group, we can just start with some sort of set T. So M is a number at least 2. So we can start with a set T which has some sort of binary operation, right? So I just assume that T has a binary operation, and I assume that sigma is a permutation of the set T. I mean, sigma in the previous slides was the inversion map. So here I'm not going to assume that there is inverse in this binary operation. I'm not even going to assume that it has identity element, but I do need some sort of permutation here. And so again, we set omega to be this set T to the M, and we can sort of define these functions exactly the same way as we have defined them on the previous slide, except, I mean, we substitute the group operation with this binary operation, and we substitute inverse with this sigma. So we define these F0j, Fi0, and Fij this way for every T in omega. And again, we sort of collect these partitions. So every map will define a partition, and we collect these partitions which start with an I into this set, which we call EI. So here, as I said, so instead of starting with a group, we start with a binary operation. So what do we need in order to get something interesting? And so this lemma holds that the first thing in this set, the first collection of partitions is going to be a Cartesian decomposition. So this is in fact going to be the natural Cartesian decomposition of the set T to the M. But in order to have, we want the other collection of partitions to be Cartesian decompositions also, and this lemma says that for I at least 1, these things are going to be Cartesian decompositions if and only if this group operation satisfies this property that for every T and X, this equation every T and S, sorry, for every T and S in this structure, so there is a unique X such that T times X is equal to S. And this is what people call a left quasi-group. So in order to get that, in order to make the other collection of partitions, the Cartesian decomposition, we need a left quasi-group. And so this is a problem that I formulated, which we cannot really answer at the moment. So is it possible to get interesting structures which do not correspond to groups? So is it possible to get interesting examples here, symmetric examples? As I said, I want probably point transitive, primitive, some other nice properties, without actually assuming that this T is a group. And we do get some interesting facts. I mean, this lemma looks a bit technical, this theorem, but it actually tells us that looking at these partitions, we can actually see whether this thing is a group or not. So when M is at least 3, so when I have at least 3 of these T's, and T is a quasi-group, so a quasi-group is a left quasi-group and right quasi-group at the same time, and then the following are equivalent. So I have these partitions, this F tilde Ij. So here, this means the meet of partition. So this is like the meet operation in the partition lattice. If I calculate the meet of each of these partitions, I mean for a fixed I, and here for every j different from 0 and I get something which is independent of I. So I get the same partition here if and only if this quasi-group is a group, and this sigma, this permutation of T, is actually the permutation that corresponds to inversion modulo some sort of constant C. So this is interesting. So it may not look as spectacular, but it's sort of interesting that you can look at the partition lattice generated by these partitions, and there are certain combinatorial properties that would force this quasi-group to be a group. And so what about symmetries of these diagonal structures? So if T is a left quasi-group and sigma is a permutation of T, as was supposed at the beginning, and we construct this diagonal structure on the set T to the M, and so there is always some sort of representation of Sm. There is always an action of the symmetric group Sm on omega, which is by permuting the coordinates of the elements of Tn. And this thing always preserves the diagonal structure. So Sm under this map would preserve the diagonal structure, but it stabilizes the first element, E0, which corresponds to the Cartesian decomposition, the natural Cartesian decomposition of this set. It would stabilize E0, and it would permute the rest of these Cartesian decompositions naturally, as Sm does. And in order to in order to get something, so we want an action of Sm plus 1, not just Sm. So you remember in the definition of the diagonal group, we have an Sm plus 1 sort of acting naturally. So what do we need? So we would need, in order to get one action, we don't know if this is the only possibility, but in order to get one action of the symmetric group of degree m plus 1 on our diagonal structure, we would need these equations to hold for the semigroup. And they are sort of, they look like associativity. So if T was a group and then sigma was the inversion operation, then these equations would follow by associativity. And in fact, it's actually possible to prove that if T has right identity, the quasi-group T has right identity, then this first equation already implies that it has to be a group, it has to be associative. But, so if these conditions hold, we can define this tau acting on omega by sort of doing this. So an M tuple, the image of an M tuple under tau would be this, so it would sort of apply sigma on the first component, and it would sort of multiply the other components by T1, the image of T1 under sigma. And if these conditions hold, then theta, this tau is also going to be an element of the symmetric. It would be an element of the symmetric group on omega. It would be an involution, and this would actually swap the first two elements in my diagonal structure. So it would swap E1 and E2, and it would stabilize the other EIs. And in particular, so this permutation tau would stabilize the diagonal structure, and the symmetric group on the previous slide, Sm, together with tau, would actually generate an Sm plus 1. So this is how we can, this is a sufficient condition to obtain an action of Sm plus 1, but we don't know if this is necessary or this is the only way of doing it. And so what we have about diagonal structures, I mean, this is a theorem that I have mentioned, at least one part I have mentioned before. So if we do have a group, so here, as I said, it's an open question for us whether can you get anything interesting from a quasi-group, which is not a group. At the moment, we don't know. And so we sort of look at diagonal structures that correspond to groups. So if T is a group and then your set is T to the M, so in this case, because of associativity, you are allowed to act by t to the m on your underlying set by right multiplication and by t by left multiplication, and then you do get that these maps preserve the diagonal structure. So in this case, so if T is a group, then the full stabilizer of the diagonal structure inside the full symmetric group is going to be this diagonal group that we had introduced before, and its structure looks like this. And I would like to emphasize that this is true even if T is infinite, so it doesn't have to be finite. And also, at the moment, I assume that T is not abelian. We had some conversation about it this morning, that maybe it's not a necessary assumption, but let me just say it this way. So if T is non-abelian, then the following are equivalent. So this diagonal group is primitive if and only if it's quasi-primitive, if and only if this group T is characteristically simple. And this is also true, this result also true without assuming that T is finite. So we do get, in this case, an interesting class of infinite primitive, quasi-primitive permutation groups. Chapter 4, diagonal graphs. I said, so we get this diagonal group acting on this diagonal structure, but it also has an interesting graph construction on which this group acts, and this I find particularly interesting. And let me remind you, before showing you this graph, that when we have the least product in product action, it stabilizes this Cartesian decomposition, but it can also be viewed as the automorphism group of the Hamming graph. And the Hamming graph, in case you don't know, I'm sure you do, so the Hamming graph is a graph whose vertex set is a Cartesian power of some sort of smaller set, gamma to the m. So this is the vertex set. The Hamming graph is usually denoted by hm gamma. And so the vertices are elements here, and adjacency in this graph is defined by Hamming distance 1. So we have that two such m tuples would be adjacent if and only if they differ in exactly one coordinate. So their Hamming distance would be 1. And this is an undirected graph, and it's called a Hamming graph. So this adjacency condition can be expressed in a more complicated way using these partitions, but I wrote it down because this is what we sort of need in order to take it over to the diagonal, to construct the diagonal graph. So adjacency in this Hamming graph can be expressed using the corresponding Cartesian decompositions. So we say that the two vertices alpha and beta are adjacent if and only if they belong to the same block in exactly n-1 of these corresponding partitions. So this is another way of sort of describing adjacency. And it's well known, although not so easy to prove, that the full automorphism group of the Hamming graph is actually equal to the full stabilizer of the corresponding Cartesian decomposition. And it's actually the least product of two symmetric groups in product action. And so we can sort of take this to the next level using the diagonal group. So what do we do to construct a similar graph for the diagonal group? So we start with a number m at least 2. So we assume that T is a group. And again, here we consider the sigma. So our sigma map will be the inversion. And so we consider the corresponding diagonal structure, D, DTM, which in this case contains Cartesian decompositions, m plus 1 Cartesian decompositions of the underlying set. And each Cartesian decomposition determines a Hamming graph. So each of these E's, E1, E0, E1 up to En, determines a way of writing the underlying set as a direct power. So each Cartesian decomposition will determine a corresponding Hamming graph on the vertex set omega. And what we do is that we just take the edge union of these Hamming graphs. So this is what we denote by gamma d. So gamma d is the edge union of these Hamming graphs, and this is the diagonal graph that corresponds to this diagonal structure. And there is a simple lemma that it says that, so you consider the edge union of these Hamming graphs, but there is a lot of overlap between these Hamming graphs. So what you really need in order to consider the edge set, so two such vertices would be adjacent in this graph if and only if one of these conditions hold. So either I have that they agree in exactly m-1 coordinates, which would be exactly the adjacency condition in the Hamming graph, or there is some sort of t in my group such that the second vertex is actually just a translate of the first vertex by this thing t. And so it's also, this lemma says that even though this graph is defined as the edge union of m+1 Hamming graphs, you really need one of these Hamming graphs and an extra family of edges. And again, it's an interesting thing that we proved that the isomorphism type of this graph determines the number m, the number of these coordinates, and the isomorphism type of the group T. So it's interesting that whereas for the Hamming graph, you get the same graph if you are given the size of the alphabet and the number of coordinates, you get the same graph, whereas here, different groups will give you different graphs. And if m and t are different from these numbers, so excluding a small number of very small cases, the automorphism group of this diagonal graph would be equal to the stabilizer of the diagonal structure, which is equal to our diagonal group, which has this sort of structure, as I had shown you on a previous slide. So, and again, I mean, this holds also when t is infinite. So we get, using infinite groups, we may get like a family of infinite graphs which have interesting automorphism groups. And let me just say 2 words about the proof, because isotopy came up yesterday in Josh's talk. And here, the proof of this theorem goes by induction on m. And the first case, when m is equal to 2, then what we have is the so-called Latin square graph. So the Latin square graph is the graph whose vertices are sort of cells in a Latin square, and 2 vertices are adjacent if and only if they are in the same row, same column, or they have the same label. And this is the case m equals 2. And the Latin square graph determines the underlying Latin square, which can be considered as a quasi-group up to paratopism, which is a generalization of isotopism. And there is a theorem by Albert from the 40s, which says that the 2 groups are paratopic if and only if they are isomorphic. And this is what lies under the first case of this induction when m is equal to 2. So it's an interesting connection with the talk yesterday and also with the comment by Bill that was made after. So we get that this diagonal group now is the full stabilizer of 2 interesting structures, the diagonal structure and also this graph. And it has some applications already. So this is really chapter 5 in my talk. I still have some time, right? In a couple of minutes. Yeah, so I want to show you 2 applications that are by Peter and his collaborators, in which this graph has already featured. And the first application is in a paper by John Bray, Kai, Peter Cameron, Pablo Spiga, and Young, that was published, I think, in the Sims volume.
Yes, so the actual date is 2020.
Right. I mean, I put in the date of the preprint.
Yes.
Yeah. So that was that's a recent result, which says that if you consider the diagonal graph of a finite simple group, then the chromatic number and the clique number of this graph are equal. And this is interesting because this is a sufficient and necessary condition for a permutation group to be non-synchronizing. And I'm not gonna, you probably know what non-synchronizing means. So this was an open question for some time, whether groups of simple diagonal type are synchronizing and non-synchronizing. And this result implies that in fact, so finite primitive permutation groups of simple diagonal type are non-synchronizing. And this is based on this result. And And this is actually not so easy to prove, because one case, I think you have to consider the case when the number of coordinates is even and odd, and the coloring in one case is sort of easy to construct. In the other case, the construction of the coloring relies on the validity of the whole page conjecture, which is proved in the same paper for finite groups. And the conjecture, now it's a theorem, right? It's proved, but the theorem states that a finite group admits a bijection sigma that has this property that this map, which maps G into G times the image of G under sigma, is also a bijection. And such a map is called a complete mapping. So a finite group admits this complete mapping if and only if CLO2 subgroups of G are not cyclic.
Or are trivial.
Or are trivial. Right. So if it has odd order,
Yes.
that would be okay.
So if you regard this trivial group as cyclic, then you have to put that in.
Sure. So this is one application in which a recent result, in which this diagonal graph is explicitly featured, and another interesting application also by Peter about association schemes that in a paper which I think was published also in 2019.
Yes.
2019, so it's a recent paper. States that groups of simple diagonal type, so primitive permutation groups of simple diagonal type, preserve association schemes. So there is an explicit association scheme constructed for groups of simple diagonal type, and the relation between this association scheme and the simple diagonal graph is that so association scheme is a set of relations that satisfy certain properties, and one relation in this association scheme is actually the adjacency relation in the simple diagonal graph. So the graph sort of appears as one of the components of this association scheme, and is led to this corollary that an AS-free group, or a group which doesn't preserve association scheme, has to be, like if it's finite, it has to be primitive. It can't preserve a Cartesian decomposition or a diagonal structure. It has to be either too homogeneous or almost simple. So this gave a complete description of groups that don't preserve association schemes. And I think this is what I wanted to say today. Thank you.
Csaba, other questions, comments, problems, where to go next? That's quite a lot of new work. Questions?
Crazy question. Is it impossible to imagine that if you had one of those almost simple groups, primitive almost simple group, that there is some element in, say, P5 omega or something like that, P6 omega, etc., such that that group is the stabilizer of that element?
No, it's not impossible to imagine.
Likely true. Most almost simple groups, maximal ones, are automorphism groups of graphs and things like that. So they bring something in P2.
Yeah, there might be. So for instance, if you take P omega 8 plus with certain outer automorphisms, it wouldn't preserve a Cartesian decomposition, but it would preserve a set of 3 Cartesian decompositions, permuting them around, inducing a full symmetric S3. But I don't think that would give us a diagonal structure in this sense. But it's in a sense is a similar object, for instance.
But it's less likely that there would be a sort of a uniform K such that every almost simple group naturally was doing something inside
yes.
iterated P to the K.
I would conjecture that K is 3 or possibly 2. Because the diagonal groups, I mean, Chaba's shown them in P4, but actually they lie in P2 because they're the automorphism groups of the diagonal graph.
Right.
Right.
So you can flatten them down.
You can flatten them down, yeah.
Yeah.
That's right. So I wouldn't be surprised if 2 was the right answer, but 3 almost certainly would be enough. See, M24, for example, is the automorphism group of the Steiner system.
Yeah.
That's a set of 8 sets, so simply 2.
Yes.
That's about the most combinatorial simple group you can make.
You know, if you take any simple group which is not too transitive, it would be some G-invariant graph. Because it's maximal and symmetric, it's the full automorphism group of that graph. So all of those are in group 2. Almost simple, it's not a problem. And we've done all the other types, right?
Yeah.
So the answer to the question is yes, there is a bound.
It's 2.
Well, it might be 2, yes.
Well, maybe you
Check.
couldn't have proved the maximality with just looking at the graph.
Absolutely, absolutely. I mean, but on the other hand, once you've got it, you can use it.
Can I go another step further and you say if we give you any subgroup of symmetric omega, can you find some element in some p to the k such that that subgroup is a stabilizer of that kind?
Any subgroup.
There's
Yeah,
a theorem
like
that
weird free construction.
so any group can be realized as a graph automorphism.
Yeah.
But it would be a nice
Yes,
graph.
but not as a
Almost
permutation, not as a permutation group.
Yeah.
You have to have many orbits to do that.
Yeah.
No, something like that's probably true, but you might have to work a bit.
Yeah, I mean, surely if you went far enough, you could actually encode the permutations in the group almost.
Well, yes, but then it wouldn't be a finite bound. Can I just make one comment about something completely different, namely this theorem up here? Some people here might know about the Weisfeiler-Lohmann algorithm, graph stabilization. So what I really strongly believe now is that this association scheme that Cheryl and I constructed is the Weisfeiler-Lohmann stabilization of the diagonal group. And that would be a nice characterization of this. So I'm pretty sure that if you held a gun to my head, I could write down the proof of that.
I'm about to ask you to join me in thanking Csaba again, but first you are all invited to watch wine.
Cheese and wine over them has been